All right, welcome back everybody to the next talk in our 3D Geometry and Vision seminar. We're very happy to have Siyu Tang here, who is an assistant professor at ETH Zurich in the Department of Computer Science. And so prior to that, she already had her own research group at the MPI for Intelligent Systems, and she received her PhD from the MPI for Informatics with Bert Schiele, and her research has also been recognized already at this young stage with a few awards, including the Ellis Award for her PhD thesis. And so Siyu does a lot of really forward-thinking, cutting-edge research in terms of analyzing videos and people and how to understand scenes as a whole with the interactions between people and objects and in scenes. So today we also have guest panelists Gerard Ponsmall and Omar Hillegas, as well as Torsten, who will be with us. And so Siyu would be speaking about generating people interacting with 3D scenes and objects. And at the end, we'll have a bunch of questions. So for those on YouTube, please feel free to ask any questions in the chat during the talk, and we can discuss them afterwards.
Thank you very much, Angela, for the introduction. I'm very happy to be here to present our works. So today I will be presenting the topic about generating people interacting with 3D things and objects. And you can see on the images, on the right images are the generated people from one of our works. So first, I would like to talk about motivation, and hopefully I can convince you this is a super interesting and important task to work on. So first, in recent years, there are many high-quality data sets of 3D indoor things has been proposed, such as Metapod 3D and Replica and many others. So they use 3D scanning and reconstruction technologies to create 3D environment. And also embodied agents exist inside this 3D environment, for example, such as habitat simulators. And probably lots of people have seen this video from Habitat. And I think these are all great research directions, for example, to do scene understanding from embodied view and autonomous navigation and so on. But if you take a closer look at this environment, I think a significant limitation of them is they don't really contain people. And the reason such world contains no people is that there is no automated tools to create realistic people interacting realistically with 3D things. And I think manually doing this requires significant artist effort. So therefore, an ongoing research directions in my group is to automatically generate natural and realistic 3D human body models, bodies and motions in this environment. And speaking about artist effort, 3D content creation is needed, for example, for video games and VR applications. And this is a slice from Andrew Price. So like you can see, like 3D assets are very, very expensive. And at least partially automating such process could largely reduce the cost. And I think if you follow this seminar, I have been following this seminar, it's an amazing seminar. So from, I think the talk from Nilo Mitra also showed this kind of image about 3D content creation for objects. And I think also one important aspect is the creation of people in this 3D environment. Another application I would like to mention is synthetic data generation. So this is a slice from Arrowwood from Microsoft. And all these hands actually are generated images for learning hand recognition method. I think they look great. And I think there are many benefits to use synthetic training data. For example, to handle long tail distributions, For example, if we think the hand recognition method is not good for a hand with tattoos, and then we can easily generate many training data of hand with tattoos, right? And also, for example, dance supervision. With synthetic data, we can really train per pixel depth, and also like 400, 500 key point for a single hand, which is impossible if you have a real world images and you ask people to annotate that. And this is how these beautiful images are made according to Arrowwood. So basically they have a parametric 3D model, and they have a pose data set, they have wardrobe, and in the end they have a render. So from my point of view, I think the 3D, like the pose data set, is one of the limitations of this pipeline. So what they have to do is to have lots of motion capture of hand poses, and then to render this, when they want to render or pose the parametric 3D hand models, they randomly maybe choose some poses from the pose data set. But what if we want to have the hand interacting with object, or hand interacting with each other? For example, interacting with objects, there are thousands type of objects in the world, right? And exhaustive motion capture is, I think, is near impossible. And if we have an automatic way to generate realistic hand interaction with object, and I think this really will scale up this synthetic data generation process, right? Okay, so hopefully I convince you this is an interesting direction. And the next thing I want to discuss is what is a challenge? So why people haven't been able to do such tasks? So we ourselves, we interact with the world surrounding us all the time, but maybe we don't realize how complex these interactions are. So these examples are from the PROX dataset. By the way, I think this dataset is super cool. It contains 3D scans of 12 rooms and use the RGBD camera to capture how humans interact with this room freely. And you can see like what really makes this interaction really challenging. There are different aspects. For example, articulation. Human bodies are highly articulated. If you look at these images, how do different people sit? And people really have creative ways to interact with the world. They do stretching, they lying on the floor, maybe they sitting on the table. So it's highly articulate. They have highly articulated poses. And second, body shapes also play an important role in terms of the interaction. So given different size, for example, a person with a bigger body moves differently compared to like a single person, right? And what makes modeling interaction even harder is a huge variance of 3D scenes of object. Just in this 12 rooms, there are all kinds of sofas, there are all kinds of chairs, there are objects, and how to really have a good feature to model human interact with this huge variance of 3D things of object, I think is extremely challenging. And of course, we want the interaction to be physical plausible, right? For example, people should have no interpenetration with the environment. And when people have interaction with the environment, they should have proper contact. And also we want the interaction to be semantically plausible, right? So basically we have a purpose when we use some object, and this semantic meaning, we hope we can also build into the interaction models. Okay, so in order to tackle these challenges, so in last year in my group, we have proposed we have worked on 3 different projects, and in this talk I will present these 3 projects. So in the first project, we basically, it's an exploration in this direction. So we propose a simple generative model, and we also have data set and also propose evaluation metrics for the tasks of generating realistic people in the scene. And in the second project, we propose a new human interaction representation. So given this new representation, we were able to generate quite realistic human bodies given 3D environment. And in the last experiment, we explore how to model hand-object interaction. And we go from the sparse features, which proposed in the second project, go to really dense features. So we use sign distance functions to model hand-object interaction. So let's first look at the first project, generating realistic humans for digital world. So let's start with related work. We are not the first one to synthesize human interactions. There are many previous work, here I want to highlight two very interesting ones. So the pie graph work on the left, proposed in SIGGRAPH 2016, I think, learns a model connecting human poses and the arrangement of 3D objects in the scene. They have a way, they propose data sets, they also propose learning method. I think it's very interesting. And on the left is a work from CVPR 19. So they use a 3D body synthesizer to generate training data by learning to put human stick figures in an environment. So while all these works are very interesting, I think a limitation here is body representation. So with the stick figure, like skeleton representation, it's very hard to model detailed human-scene interactions, and also to model collation and contact in a physically and semantically plausible way. And so here is the result of our work, which was presented at CVPR last year. So given the 3D scene, our model aims to generate realistic bodies that interacting with the scene realistically. Briefly speaking, our solution is inspired by how humans infer plausible interactions with the environment. So when a human enters a room, the interaction plan might depend on the structure and the semantic of the room. And afterwards, to realize these interaction plans, physical rules may apply to determine the detailed human object configuration. Therefore, our method has two steps. So the first one is a probabilistic human body generator, and the second one is interaction-based optimizer. And in the following slides, I will talk about the details of these two steps. So here's the method overview. You can see, given a 3D environment of the scan, we have a fully automatic system that takes this 3D environment and generate human bodies. And as I said, for the first step, we have a learning framework. So it's a scene context-aware human body generator. It's basically a conditional variational autoencoder to generate human meshes. And for the second step, we have a geometry-aware fitting. So it's optimization steps to refine the human-scene interaction. And so let's first look at the first step. To design this body generator, the first question we have is how to represent the scene and how to represent the body. So we represent the scene from the view of embodied agents. So we use the view like in the habitat simulator. And we capture the scene depths and semantics as our scene representation, because we think they are very valuable modalities for scene understanding. And for each view, we basically have a stack of the depths and the semantics, and we note this as xx as a scene representation. And for the human bodies, we use a simple X body models to represent 3D human bodies. And for people who don't know simple X body models can be considered as a function mapping from a group of low-dimensional body features, XH here, to a 3D body mesh. And this body features XH consists of the global translation of the body, global orientation, as well as the pose, body pose, hand pose, and shape parameters. And based on these representations, we propose a generative model of human-scene interaction, basically using a standard conditional variational autoencoder framework. So you can see we concatenate the depths and semantic images, and then we have an encoder for that. And we also have an encoder for the body meshes. And then we concatenate these depths and semantic features into the encoder and decoder. And we train a VAE basically to generate plausible bodies during the inference time. So you can see here is the inference pipeline. Given an empty room, we have an embodied agent to capture the depth and semantic images. So we have the feature for that. And then we random sample the from Gaussian distribution, and then we concatenate these random samples with these scene features to generate the body parameters. Okay, so the sampled human body sometimes has physically impossible configurations. So for example, floating or slightly collision with the environment. In the second step, we refine the body meshes with the optimization step. So in this optimization step, we encourage contact and we try to avoid collisions. So in the details of this optimization objective, so the first, okay, so the first XH and XH0 basically means the target body configuration should be as close as to the generated ones. And then the second and the third ones are the human scene interaction loss. So we basically use the contact loss and interpenetration loss from the Prox paper at ICCV 2019. So the idea they have is for the collisions, basically they have a scene SDF and they try to minimize the negative sign distance for the body vertex. So basically if the body is in the scene SDF, they try to push the body out. And for the contact loss, they have a heuristic contact map on the bodies. So for example, the foot and also the back of the body. And if the body is, this body part is close to the scene vertexes, they have a contact term to try to minimize the distance between the body vertex and the scene vertex to enforce proper contact. And the very last one, this Weiposer loss, is basically a regularization of the plausible human body poses. Okay, so that's basically about the model. The next, I want to talk about data set and experiment. So as we have this model, we need training data. So basically what we train is on the prox, we extend the prox data set. I will talk later in the next slides. And besides the prox data set, we also test on the Metapod 3D data set where there is no human in the data set, right, captured. So in order to train our method, if you remember, we need virtual agent, right, to capture depths and the semantic maps from a view from a virtual camera. And the original prox data set, the 3D scene scans are not complete and they don't have semantics. And what we did is basically we add the ceilings and the walls to the prox data set. And we also manually annotate the mesh vertices to have the semantics. And in the end, we add virtual cameras in each room so we can get lots of training images from virtual cameras. So by doing this, we can really utilize this. So prox has 12 things. So we can really use 12 things to train and generalize well to the Metapod 3D dataset. And another challenge in this work is a baseline. So we don't find any really baselines to generate realistic human bodies in the environment, right? So what the closest work we find is this work from putting people in a scene from ICCV 19. And in order to have a fair comparison with them, we did lots of modifications. So basically, we changed the scene representation from RGB to depth and semantic maps so that their method can be trained and generalized on the prox dataset. And for the geometry aware discriminator, we project the mesh vertices rather than the stick figures, which I think improves the performance. And we also combine their model with our geometry aware optimizer. And you can see this is a result with our modifications from the baseline. And we think like the result looks quite nice with all these modifications. And the last challenge of this work is how to evaluate this method, right? This is a kind of a new task. How do we do the evaluation? So we basically propose a diverse set of evaluation metrics to quantitatively evaluate generative models. So basically it includes the diversity metrics. So this metrics aim to evaluate how diverse the generated bodies are, right? Given a room, we don't want the body just standing in the middle of the room, right? We want the body to be really everywhere, to sit on the sofa, to stand on the corner, to leaning on the wall. So have different body poses. So this is the diversity. And another important aspect is a physical perspective. So we also evaluate the correlation and contact between the body and mesh to evaluate like how physically plausible the generated bodies are. And I think the most important metric among these three is a perceptual study, large scale perceptual study, right? If we draw random samples and then we really render lots of random samples and we give this to a large amount of users at AMT to evaluate our method, like the generative method. I think this is a very important metric to really evaluate how realistic the generated human bodies are. And a very interesting experiment we did in the end is to use this generative model. So you can consider this like a scene conditional generative model, right? To use this generative model to improve the 3D pose estimation result. So basically, we go back to the recognition task. We see, okay, now we have a generative model of human-scene interaction. How do we improve the 3D pose estimation? And then this was the last experiment we did. Okay, so due to the time limit, I will show you the number, like the performance on the perceptual study. So on the left is a human-scene interaction, like interface we put on the AMT, and we ask lots of users to evaluate like our method. So we compare with the baseline. We have our model. We also compare with the ground truth, also on the prox dataset, because prox also captures the real human-scene interaction. And you can see actually the baseline performs quite well. Our method is a little bit better than the baseline on the proxy dataset, and I think the baseline and our method are really comparable on the Metapod 3D dataset. And there is a huge gap to the ground truth. So basically, users still really can recognize ground truth, like the captured human-scene interaction, is much more realistic than the generated ones. Yeah. And this is a VR demo we included. So we did. So basically, we put this as I think this is maybe a replica thing. I'm not 100% sure, but we generate 3D bodies on this environment, and this is a view of the like VR. You can see the on the left corner, up corner is our colleague. And then he's really wearing the VR glasses to see the human-scene interaction, but you can still see there are interpenetrations between the body and the environment. And there are still quite some failure cases when we sample from the conditional VE model. And the optimization steps also have limitations, doesn't really help realism. So the next question is how to make this generation process more stable. So let's go back to see these examples, right? How humans interact with the environment. I think human interaction with the environment is really like rooted in the contact. So different interactions has different distance, have different contacts with the environment. Then how to really directly model the distance between the environment, like the geometry, and the human body. I think if we build our model directly on these features, it will really improve the performance. So basically, that's the motivation of the second work. We call it place, proximity learning of articulation and contact in 3D environment. So before go to the feature we proposed, the interaction feature we proposed in this work, I want to first introduce this idea of basis point set. So it's a work published in ICCV by Sergey, published in ICCV 2019. So the idea, this basis point set is basically what they use is to try to register the point cloud into a human body. So the input to their method is basically all kinds of human body, like human body point cloud. So this is just one point cloud human body, right? And what they want to do, the output is a location, like XYZ location of each vertex of a human body model. Here they use simple. And then you can see on the left, can you see my mouse? Yeah, okay, good. So you can see on the right image, on the left image. So basically what they are interested in is to modeling this point cloud of this human body, right? But they have another set of point. They call it fixed point, like a basis point set. So this point, this red dot, they don't change. They are fixed in the space. And then how do they really encode this point cloud of arbitrary bodies, arbitrary poses? They basically compute the distance from this fixed basis point set to the closest distance to the point cloud of human body. So basically for each point cloud of this human body, they have a fixed, like they have a distance-based feature. And here they use a 1022 dimension. So basically because they have 1022 fixed basis point, right? So for each basis point, they have a distance to the underlying point cloud of the human body. And then they have a very simple MLP to regress the vertex location of a human body model. So I think this idea is very cool, it's very simple, but very effective. And what we did is we basically try to extend it to the, so basically our human scene and interaction representation is inspired by this distance-based representation. So our key ideas is given a scene mesh, right? A 3D scene environment and a human body mesh. So we can have the basis point on the scene body, on the scene vertices, right? And then basically we can have a set of distance-based features. Each dimension of these features is the distance from this fixed set, from this basis point on the scene to the closest point on the body, right? So we call this BPS interaction features. And you can see, like, given a fixed set of points on the environment, and different bodies actually have a different set of distance to this fixed body point. And you can see different poses really have different BPS features. And given this feature representation, basically what we design is a human body generator based on variational autoencoder. So you can see given a body and a given environment, we have a human body, again from a prox data set, and we have a distance-based features. And then we have a VAE to reconstruct this body features. And then we have another MLP to estimate the body vertex locations. And basically now our generative model is not generating body parameters directly. It really generates the distance of the representations between the body and the environment. And during the inference, right, given the same environment, what we have to do is draw random samples from Gaussian distribution, and then we give it to the decoder. It generates a set of plausible distance between the body and the environment. And from this distance, we infer the body vertex locations. And turns out this works really, really well. So we were really happy with this, like this simple VAE model can generate plausible. So these are the generated human bodies given this environment, right? The human looks really relaxing, right? Sitting on the chair. But you may notice, like, this simple model doesn't work for multiple things, right? This model only works for single things because we have a fixed set of basis points on the scene mesh. And then the next question is how do we generalize this to different things? So there are two questions. How do we select the basis point on different scene meshes? And the second question is how do we encode this basis point on the different scene meshes? So basically our idea is we propose this two-stage distance-based human scene encoding. So the idea is we have a fixed set of basis points in space. You can see all these dots are the fixed set of, so they don't change for different environment. They cover the whole environment. And this point can be randomly selected, but they have to be fixed for all the training and test environment. And then we use the minimal distance between this fixed BPS in the space and the scene meshes, the scene mesh vertex to encode the environment. So you can see these are all the different environment, and we use a fixed set of BPS to encode the scene. And then the selected vertices on the scene mesh are the basis point to encode the human body. So you see this two stage. Okay, for all the environment, we have a fixed set of basis point. We use this point to encode all kinds of different environment. And then for the selected vertices on the environment, we use this to encode different bodies. So this kind of two-level distance-based features. And then how does this works for arbitrary environment? So given a pair of scene and a human body, we have this fixed set of BPS on the environment. We have this distance-based features to represent the scene. And then based on the selected vertices on the scene meshes, we have another distance-based features to encode the body, right? And then what we did is for the scene BPS, we just have an autoencoder to have a latent representation for this environment. And for the BPS features, basically is again a conditional variational autoencoder. We put this latent representation of the environment of the scene, right, to the encoder and the decoder. And then given the generated or reconstructed body and scene distance, we have another MLP to reconstruct the human vertices. So this is a pipeline of the body generator for arbitrary environment. And in order to have like a better reconstruction, we find out if we just encode the distance of the scene is not enough. So what we did is also for each scene vertices, we also encode the absolute XY location. So basically we have another latent representation for the environment to have a stronger environment conditions. And then we put this latent representation to the MLP. So basically give us better results. And during the inference, you can see, right? So given environment, right, we have the BPS, we have a latent representation, and we also have a latent representation for all the scene vertices, right? And then to generate the bodies, we draw random samples from the Gaussian distribution. We can generate the distance between the scene and the body conditioned on the environment. And then we later, in the final stage, we regress the body vertex locations. So this is the inference stage for this generative model. And it works quite well. I think from our observation, it's much more stable than the CBPR work. So I think because this really the whole generative model is built on the direct interaction representation, so the distance between the body and the environment. This makes the whole generation framework much more reliable and stable. So after the generative model, right, what we get is basically scene vertices, right, location. So it doesn't really give us the body parameters beta and theta. So you can see on the top as a result from the generative models, what we get in the end is just the location of each vertices, right? You can see the body surface is not really smooth, and sometimes we don't have really valid body shape. I think I have example later. And again, we did this interaction-based optimization. On one hand, it can help a little bit with this interpenetration case. And on the other hand, we really get the human body model back with the parameters, pose and shape parameters. And for this, we test on 3 different data sets. So besides the prox and Metapod 3D, we also test on the replica data set. And we compare against like our previous work. And I want to highlight this perceptual study. We were very excited about this result. So basically here we did like a very direct comparison. So we put like pair-to-pair comparison. So we put either like the CBPR work and this work, or this work and the ground truth, right? And you can see when we compare with the CBPR work, PSI, right? Like it's a significant improvement, right? 70% of the users really consider this work is much more stable than the CBPR work. So both are really random samples from the model. And when we really compare with the ground truth, this is very encouraging, I think. So we have random samples from our model, and we also random sample one from the ground truth prox captured human body. And you can see our result is really close to the ground truth result. And these are random samples. So we were very much encouraged by and also very exciting about this result. And here I want to show the latent space interpolation. So on the left most and on the right most are two samples, I think random samples. And you can see if we walk, like interpolate in the latent representation, and you can see actually the persons really like naturally interact with the environment based on the location, right? It feels like this person is trying to sit down, right? And you can see there are also, I mean, this is a failure case I mentioned, right? The result from, first of all, these are the result from the generator without any optimization, right? And you can see this is not a really valid body shape. So because this is just vertices of the body model, right? And you can see when the person is close to the bed, is trying to sit, and when the person is close, like sitting on the floor, is basically just standing. Yeah, and even trying to sit on the table. So these are the result, and there are more results on the, I think these are the replica data set and some of the prox data set. Yeah. Yes, so that's the second part, the second project. And in parallel, actually, we were, after the CBPR work, we were also very interested in the like hand object interaction, right? So these people, like if you take a look like the prox data set, right? People not just interacting with the 3D environment, people also interacting with object constantly. For example, I'm holding this pen, and how to model this, like this interaction with like detailed object, this small object is also very, very interesting for us. And it's very important for this generating realistic human bodies interacting with the environment. And to make the task slightly easier, so in this work, we only focus on the hand object interaction. And you can imagine this should be extended to the full body and object interaction. But for this one, we really focus on the hand object interaction. And the question we have here is, so you can consider this BPS distance-based representation is a kind of sparse interaction representation because we only select point of the vertices on the surface, right? And it's a distance-based representation, it's 1000 dimension, it's a sparse representation. And here, I mean, I personally think when we really model hand-object interaction, for example, this kind of interaction, we probably need to go to really dense representation, right? Because object can be really small, like interpenetration and contact has to be handled really well. And then we might really need to think about how to have like even continuous representation of interaction between the hand and object. So that's the motivation of this work. And we call it grasping field and learning implicit representations for hand grasps. So first of all, I want to show the result. Again, we are excited by the result. So these are the generated human hand given different object. And you can see this object has different shapes. They have different geometries. And I mean, our general grasps are not perfect. So not here, there is no really like interpenetration and contact optimization here, right? We don't really, if we have interpenetration and contact optimization refinement, this will be again even better. So now you can see there's some like maybe not perfect contact between object and the environment, but this is just purely from the generative model. So we were quite excited about this this work, and we think the key reasons it can achieve such kind of performance is really the representation we learned and we used to model this task. Okay, so first of related work, hand-object interaction is of like wide interest from robotics to computer graphics to computer vision. Like it's a really important task. So it has been studied everywhere, right? And our key insight is human grasps is rooted in the physical hand-object contact. So through this contact, humans are able to grasp and manipulate objects naturally. So to better model hand and object interaction, we must find a way to effectively and efficiently to represent the contact between the object and the hand. So based on this observation, what we propose is a novel interaction representation that based on regressing a continuous function that we call a grasping field. So this GF grasping field. So the idea of this grasping field is very simple. It maps any 3D point in space, for example, X, Y, Z, this 3D point, it maps any 3D point in space to a 2D space, where each dimension of this 2D space indicate the assigned distance to the hand and the assigned distance to the object. And in this way, the contact and the interpenetration relations between the hand and object can be explicitly represented. So in the next slide, I will show an example. And we further, so basically in like many other works, recently in the computer vision literature, right, we further use deep neural networks to parameterize the grasping field. So basically, we use the deep neural networks to parameterize this grasping field function, and we learn it from the data. And as a result, so this learned grasping field you can consider is a powerful representation to really use for hand object modeling. And I think one can even one can really consider this as an interaction prior. And as we showed in our paper, this interaction prior enabled us to infer various grasps of hand given object, and it also helps like reconstruction tasks. Given an image, building on top of this interaction prior, we can get good hand object reconstruction. So here is about like why this grasping field is like it has an explicit representation of the interaction. So basically, So basically this distance, right? Distance itself, the distance to the hand, the distance to the objects and distance itself tells us the surface, right? So basically this surface, the surface of the hand and object is built into this distance. And furthermore, if two distances are both smaller than 0, it means this point is really, this 3D point is really the interpenetration of the hand of an object. And if these two are both larger than 0, it means there is no contact. And for the contact surface, it's really when the both distance equals to 0, right? So basically, we can infer the contact interpenetration even before we have the surface. We extract the surface. This is different from the mesh representation. If we see like the mesh-based human hand reconstruction, you first need to reconstruct the hand mesh, and then you compute interpenetration and contact. And here, the hand surface, the object surface, 3D surface, and the interpenetration and contact regions are explicitly built in the same 2D space. So this grasping field function enabled us. And the task I want to show here is a grasp generation. So what we have given to our model is a point cloud of object. And what in the end we inferred as we generate a plausible hand poses. And here is a model. So basically we have a object encoder. It's a point cloud object encoder. We have a latent representation for the object. And during the training, we also have the hand point cloud. And then we use this hand point cloud encoder to encode the hand. And then we have a KL loss to try to learn a good latent space. And then for the decoder, it's basically our grasping field. It's not just, I mean, in the beginning, I showed like very simple representation of this grasping field, just the point. Input is a point, and the output is a two-dimensional vector distance to the hand and the object, right? But in this training, in this generative setting, besides the point, what we also put here is the condition information. So object, right, and the hand, right? So basically, this grasping field takes object latent representation and the hand latent representation, and also the query point give us the distance of this query point to the hand and to the object. And during the inference time, so again, we sample from the Gaussian distribution. And then on the other hand, we have an object condition which we have an object encoder Z0. And then all this information goes to the grasping field decoder. And then this grasping field gives us the distance of the query point to the object and to the hand. And one thing we add on top of it, because in the end, we have a distance field for the hand, right? And we can do matching cube to get the hand meshes, but the hand meshes is not really guaranteed to be like super nice, a valid hand. There's no guarantee for that. It's just a some distance field for a hand. And what we did is we tried to also fit the manual model without interpenetration and contact optimization, just fit the manual model to the matching cube output. And in order to do that, we basically have a hand part segmentation. So basically, this is a manual hand, and we also have the hand segmentation. And for our grasping field, besides the distance to the hand and object, we also have a label. So saying if this point is on the hand, and then what kind of part label it is, right? And then basically this semantic segmentation really makes manual hand fitting easy, very straightforward. So you can see this. On the left is the result by extracting the mesh from the matching cube. And you can see the surface is not very good because in our SDF, there is no notion of hand, right? So the fingers can be a bit weird. And this is what we get after fitting the manual into the matching cube by using this segmentation labels. Yeah, and for the experiment, so basically we compare with a ground truth. So for the Upman and for the FHB dataset, we have the ground truth. We also compare with the baseline where we don't generate the distance, we generate the manual parameters, basically pose and shape parameters. And sorry, you can see like for the perceptual study, I think it's very good. So it's close to it's not yet ground truth yet, right? But it's close to the ground truth. And the baseline has a very low score because just given an object to generate manual pose and shape parameters is really a challenging task. And also for the physics simulation, we are much better than the baseline. And we have a slightly worse intersection volume and depth, but we have a much better contact ratios compared to the baseline. Yeah, so that's the last work. So here's a summary. In this talk, I present 3 projects. So the first project is for us is exploration. So how to really generate realistic human bodies realistically in the environment. So we have to think about data set, we have to think about model, the representation, the evaluation metrics, the baseline. So that's like the first author Yan did an excellent job to manage to do all these kind of different challenging tasks. And for the second paper, we basically focus on the really learning what is a good feature representation for interaction for human and environment. And in the third project, we focus more on the hand and object interaction. And we go from the sparse representation, interaction representation, go to this continuous representation, and we use the neural network to learn like the distance, like called grasping field for hand and object interaction. And the next slide is about like what's next. I hope this could give us some starting point for the future discussion, panel discussion. So the first step obviously is motion synthesis. Right now the body is just static body there, and how do we make them move, right? So if the person is sitting, can this person move in the room, like stand up and go to the table and sit again, right? These are all very, very interesting but very challenging tasks. So motion synthesis in the environment. And the second thing, I think what is really important is representation. So I mean, I put human representation because I think mesh-based method, like for me, I mean, just personal thing, I think it's a bit hard to model interpenetration and contact. And what would be a better representation to model interpenetration and contact, right? And here, actually, we show like we don't just build a human, we build what we are focusing on are the interaction representation between the human and the environment, and it really improves the result. So the second question is representation. And if we think about dynamically, right? So if we think about over time, and then what would be the best representation for modeling interaction over time? So it's also a very interesting topic and challenging topic to study. And then the second one, of course, is person-person interaction, right? So now it's just single person, but we human, we are social animals. we interact with each other. We are not just interacting with the environment. So how to really model these social interactions between humans is also very interesting. And the last one, I think, is more about control. So controllable generative models. So for example, now people start to think about for generating faces, right? People start to think about how to control the geometry, how to control the viewpoint, how to control the facial expressions, right? So people try to build controllable component into the generative models. But here, like we have to think about what do we mean control for this type of interaction generative models. So I think this control comes from like slightly high level. So for example, the goal would be a control, right? And yeah, so for example, if my goal is to grab a cap, right? And then how do we generate this type of things, right? So this, an emotion maybe is a control. So this is, I think, a high level control, not just the geometry, not the like this type of things, but it's really like high level goal, this type of things. And I think there are also many others. And I hope this line of work really can encourage people. I think it's very challenging, and I hope it's really encourage people to work on this type of topics. And there are so many challenges and as well as opportunities. And in the end, I want to thank all my co-authors, and this works really like is so my PhD students Siwei and Kwarwei really did like lots of work, and also my postdoc Yan, so they are the heroes behind this work, and also my co-authors from Max Planck Institute for Intelligent Systems. And there are also many other people to help us during the whole process, and I really appreciate their help. And in the end, I thank you for your time, and I'm looking forward to the questions and discussions.
Thanks for a wonderful talk. And I think a great segue at the end, lots of interesting open questions and opportunities. So there's a couple of questions on YouTube already. Maybe we can start with some of the thoughts from Zoom. So I can start first, maybe with a question. I think, so you were speaking about representations. What's the right type of way to model these kinds of interactions? And I think the last work you presented with the hands made an argument for a dense kind of interaction field representation. Do you think that's also the right way to go for bodies? Like extending your prior work on human body interactions with scenes?
Yeah, I think it is I think it is a way to go. So so for example, detailed human interactions, for example, if I sit in a sofa, there are also deformations, right? So this type of really detailed interactions and changes of geometry, I think it should be modeled by continuous function. But before going into that direction, I think the first question we have to solve is the body representation, right? So how to really make a new representation that is good for interaction, right? To suitable for this type of continuous interaction representation. For the grasping field work, we model the hand actually as a SDF, right? Some distance field. And I think the question is, how do we really also model the body as some distance field? And then this type of like dense interaction or continuous interaction representation is somehow built in the body representation as well, right? think
Angela,
otherwise
are you going to tell
think-
us how to do this? Is everybody just free to ask questions? Or
Everybody's free to ask questions.
Everybody's free to ask
And
questions.
to interrupt.
Yeah, thank you, Siyu, for a great talk. I want to go back straight to the beginning, right, and talk a little bit about the motivation. You had a very compelling argument that to reason about 3D scenes with people in it, you first need to learn to generate them. What do you do with the generated scenes? Like, what's your main motivation? I mean, there's many possible options, right? You can train a discriminative model afterwards, or I don't know what are they for?
So the short-term goal, right, is to generate synthetic data. So it's even more on the hand level, right? If we think about hand-object interaction, the data is really hard to get, right? For example, especially in the egocentric views, how do you get the really ground truth hand-object interaction data? And if you see the slides I show from Arrowwood at Microsoft, right, this synthetic hand training data are amazing. They're beautiful, right? And then I think I'm not sure, 100% sure, but I think they really used in the product. And it tends to be really, really powerful. But what they can only do is just to sample the hand pose from a data set, from a pose data set. That's why they don't have training data. I mean, maybe they don't show, but I don't know. So at least I don't see the training data, one hand really interacting with the object, right? And if we think about interaction, this whole motion capture, this scale explodes, right? It's impossible to capture all kinds of, maybe I think it's impossible to capture all kinds of hand interaction with object. And then with our model, right, assuming we also have the motion, these kind of things, and then we can really generate realistic human hand interaction with the object, and then and with good rendering, with maybe wardrobe, all these graphics tools, right, we might really have a good data set for hand-object interaction, and we may choose the view we want, maybe egocentric views, right? So I think that's the short-term goal. And then the long-term goal is to really, I think the future is like digital. So we will have a lot more and more digital world from VR, from AR, and video games industry is growing, right? We will have really more and more digital world for bad or for good. But this digital world needs people. Otherwise, just empty world. It's not attractive. And how do we really have these people in this digital world? I don't think we have a really fully automated tools to put people inside. And there are many efforts related to this, right? So this line of work is really only about behaviors, pose, and maybe future motions. And other people works on appearance, but I think they're complementary to each other. And this pose, this behavior kind of generative model to put people in the digital world is definitely an important part of the whole game. That's my thought. Yeah, that's a long-term goal.
Yeah, lots of follow-up questions. Maybe let's stick to the first one, right? Like if you want to generate training data, how do you know when your quality is good enough, right? So maybe to give a little bit of context, we've done a lot of work with using synthetic data for eye gaze and for hands, and these are seem to be very different cases, right? Maybe we got lucky, but there's an ETRA paper where we basically used synthetic training data for eyes, and it just worked on real images. No domain adaptation, nothing necessary. For hands, this seems to be exactly the opposite. It's very, very difficult to even go from one real data set to the other and make it work. So how do you tell, or how do you predict, right, whether there will be problems with domain shift, with domain, whether you will need to do domain adaptation, whether your quality of the training data is good enough, or is this a try and see?
Yeah, so there is a parallel effort in terms of this, right? The development in computer graphics, right? It's also really like growing, like developing very fast. So if we take their moment into account, right? I think like this like how to say, so I think there is a hope to really generate realistic synthetic data. And I personally think to generate synthetic data for humans is really challenging because of hairs, facial expressions, clothing, all kinds of things, right? But for hand, I think it's more promising than human bodies. And from the result from the Arrowwood showed, I think those data look amazing, and I think they are used already in the hand recognition network. But of course, they have really good rendering method. Like this type of things has to be also very, very good. But I think for hand, it's more promising. Maybe not as promising as gates. But I somehow think it could work in the future.
Mm-hmm. Okay. Maybe one more question before I let Hira ask a few. So you approach this whole thing understandably, right? Because that's the most tractable thing, very much from a geometry perspective, right? And reason about distances and whatnot. You motivated, however, a lot with respect to interaction. And now, so what I missed a little bit, coming more from an activity understanding and recognition angle, is that seems to be missing entirely, right? That people typically do something and that has semantic meaning, right? So the angle of task and the angle of context in terms of activity seems to be missing. Is this something that you have thought about, or is this just you deliver the building blocks and then someone else does activity, or?
I hope, I'm certainly very interested in these directions, right? I guess building more semantics into these pipelines, right? But I certainly hope more and more people really working on this, because I think these are very exciting directions. So I totally agree with you. Like this, now there's so many missing pieces. For example, for hand grasping, right? Our generated hand has no ideas of object affordance, no idea of the purpose of the usage of the object. There is no such things in our model, right? And I definitely think it's super important, right? If we want a human interact with the environment object naturally, the purpose of this grasps and also the object affordance, these are things cannot be ignored. So I think with our model, with proper training data, and I think there are training data start available, we can build this component. So that's actually linked to the controllable part of the generative model, right? How to make this generative model control, assuming just the very simple cases, classification cases. If you want to use this object or you want to pass this object to others, what kind of grasps can be generated based on these two different classes, right? Just the very simple classes. This will be built in by us or by someone else, and these are the component which are super important. And with respect to human, it's similar. So now it's just the body poses, sitting somewhere, standing somewhere, super simple body poses, already challenging enough, but simple body poses. And then the next thing is, okay, if we have, for example, language, right? If we have a description about human motion in the room, right? This is kind of another controllable information, right? Like this type of things, can we generate human pose, and can we generate the motion to follow this type of descriptions, right, in the room, right? So that this person wants to, or just the goal, right? Given a person, please grab the laptop on the table, right? And then how to generate natural motion, this hand grasping, and then all kinds of things. There are so many exciting challenges, and I think that's something I'm looking into, and I hope more people also look into that. Yeah.
Mm-hmm. Great, fantastic. Hira?
Yeah, thanks. Thanks to you for this really nice talk, which you really motivated very well, and I like these papers, and I like the direction very much also.
Very good.
So first, I will start with very high-level questions and maybe get more to more technical questions. But I guess Angela or Torsten or Otmar, feel free to mix up so that it's not that boring. So the first question is quite almost philosophical. You're motivating content generation. That seems to be an obvious application. Synthetic data generation seems to be also another obvious application. But do you think that we can learn something about human intelligence by modeling how humans move around the world? I mean, it's known that intelligence evolved to move, right, and to act upon the world. Do you think it's a lot of a stretch to think that by designing computer models that can make humans move in the scenes, we can learn something about human intelligence?
Yeah, I think so human intelligence, I'm assuming like how humans think and how human interact with the environment, this type of things, right?
Yeah, so some very basic brain that can do some things.
I think that's probably the goal, right? To have the creativity in the end, right? And I think that's also like part of this games in the generative models, right? We learn lots of interactions. I mean, maybe someone come up with a motion model. We learn how human move, how human interact with this environment, right? And then we learn a distribution. We have a neural network. We have a we have some model to learn a generative distribution. And then later, maybe like when we sample from this distribution, right, we can have some creative like new interactions happens. And I think that it's not really entirely human intelligence, but that's somehow towards, right, creativity, right, this type of things. So yes, but I think for human intelligence, I'm not sure. I think it's another way of approaching that. I think it's very appealing is to learning by acting. So it's also actually follows this line of work, but it's a bit distant now, right?
Yeah.
So
yeah. So now that you mentioned that, I mean, that's why I was trying to go. So right now you're basically capturing data and learning from this data. And I think in the short term, that's definitely like you'll make larger steps. But in the long term, like, are you planning to have some component where the human or the avatar interacts automatically with the scene and sort of learns? And what kind of techniques do you see? Do you think reinforcement learning is the way to go? Or
maybe I think depends on the concrete task you want to tackle. So the technique behind that is really depends on task. But I think, I mean, there is a loop, right? Now we basically perception, we see, and we have a representation, right? And the next step is action, right? So I think there will be a loop, and with this loop, I think many people talk about it. But for me, it's also the right way to think. So now we have perception, we learn from data, we build a representation. For us, we build a representation of interaction, and then the next is how do we act, right? So assuming we can build a human body model in the simulated environment, and then I let this human body to interact with the environment, and then to update, to learn a new representation based on the interaction. I mean, there is a loop going on. I think by this we could learn more intelligence. But yeah, but the first step is to put the person in the environment.
Okay, so maybe a little bit like less high level question. So I noticed that there's no physics in your models.
Yeah.
Do you think that there should be some sort of physics?
Definitely.
Do you have some thoughts on how to do this? I'm always very afraid of dealing with physics because, like, as soon as you're not modeling some very basic rigid body dynamics, things get very complicated and nasty. But maybe that's the right way to do things. And what are your thoughts?
So I definitely think we should have physics. So I mean, we have intuitive physics now, right? By this interpenetration contact, we try to say like person doesn't really interpenetrate with the environment. It's very intuitive. And I definitely see like physics plays an important role in terms of interaction, right? Interaction is somehow really, I mean, rooted in the physics, right? So like frictions, how do you hold the cup depends on the frictions, depends on the material, depends on how heavy the cup is. If it's a really heavy thing, we have to hold it with two hands, right? And we have different body postures, depend on different weight. So there are, one can, I mean, to really go to realistic, fully realistic, right? One cannot avoid physics. That's just my own opinion, right? But I think it's a very interesting and challenging topics, and I don't have a really concrete plan or idea yet, very concrete one. But we start to think about how to use physics in terms of the motion prediction, right? People have been doing that, right, in graphics, and we are thinking like how to do, for example, build dynamic models for human bodies. I mean, as you said, like the previous like dynamic models are all skeleton, and now if you think about human mesh, and then like how do you really, I mean, for example, the external force is really not on the joint, it's on the body surface, right? And how to really build these dynamic models, these are all interesting questions, and we start to look into, but yeah, so I mean, so start look into, but we don't have a concrete idea yet.
Can I interject with a very related question? I mean, Hira already talked about like the different layers of abstraction and the different tasks necessary. So in place, you talked about the technique to generalize across different room arrangements, I would say. But if you think about what we can do, it's like an amazing feat in terms of generalization, right?
Yeah.
I can now, without seeing the outside of this building or the street outside, I can plan how to get back to my house, right? And this requires planning at very different levels of geometric and at very geometric detail and different levels of abstraction. So what's your thought on hierarchic approaches to this, right? Like, do you have to now memorize, all cities, and then within all cities, all roads, and then all buildings, and within buildings, all rooms? Or is there a way where you can kind of use this technique that I believe at the moment is limited to single rooms and kind of wrap it into outer layers of a hierarchy that would allow you to perform planning at that level of abstraction?
So yeah, so in terms of hierarchy, I mean, one thing comes to my mind, but people have been doing this quite a lot, is like for example, motion planning, right? First plan the route, right? Like the global motion, and then plan local poses to realize this interaction, right? This is one thing come to my mind. But another thing I think really related to what you are saying is this compositional thinking. Right. So, I mean, for now, we actually, I think human has amazing ability of this compositional thinking, right? So it's like we don't. So basically, for example, we don't really think like how to say, like the room is composed of chairs, floors, right, and sofas and different objects. And then this is actually in different rooms, the layout may be different, object may be different, but it's again the compositional like things, right? So how to build this compositional ability into the model, and how to design or how to learn the feature, interaction feature, based on this compositional property of object and 3D environment. I think that's a very interesting direction, and that potentially really generalize the interaction features to all kinds of different rooms, different environment.
So yeah. Maybe one question related to this, but I mean, when I interact with a chair, I only care about the chair. Well, I mean, that's not really true. I mean, there's also objects around, but I guess Otmar was pointing at how much of the global context do I have to take into account for particular actions? I mean, the reason that we generalize so well, I guess it's because we focus on one thing at a time, right? And when I'm sitting on a chair, I don't care about the rest. And so how I mean, do you think that?
I don't know. I mean, when I sitting here, I care about the window, the light. I care about, but
yeah, that's true. That's true. But to some level, like the way you sit on a chair is very similar, no matter what the environment is. So
yes.
I guess the light you think later, right? But
yes. So I get what you mean, right? So actually, that's the motivation we design this geometry-based distance feature, right? We think the local geometry is the key. It's part of the key, right? One of the key component in terms of this interaction, right? If the chair has a different geometry, we really sit differently, right? So this distance feature is really captures the geometry, local geometries, right? And I think we kind of really follow, like, have the same intuition as you said when we design this type of features.
But are you sure, right? Because that kind of depends on the exact chair. And I would argue that a human knows how to sit on a chair, can sit on any chair, right? Maybe, well, I don't know, maybe not if it's made out of nails or swords or something. But
so
most chairs,
I think another really missing component in this is the physics. Right, so when we humans see a chair, when we see a geometry of the chair, the appearance of the chair, we know like where to sit, we know how to stably sit there. And for the object looks like a chair, but not really a chair, we know, okay, we can sit there, right? So this type of things should be built into the interaction models. This is a missing component. And this physics understanding of the world makes the generalization really of humans really good. And I think if we don't have this kind of things, we probably still always have a limitation in the learned models. But just my personal opinion.
on this, so I'm always wondering, how much do you really need to learn physics, or do you just need to be able to have some sort of intelligible physics that reflect what we would expect from the world, right? Similar to graphics, not fully modeling everything, but you get by faking some things. And maybe it's a question of training data, because all the data that you have will be to some degree physically correct. So if you would have a large enough amount of training data, then I guess you would get this baked in.
I mean, this is a hard question. This is a really hard question. I mean, I don't know. I always want to capture data, not just from the visual images, right? So nowadays, like this grasping data, like for example, what if we have sensors, touching sensors, pressure sensors on the object, right? And then it will give us more information, right? For example, we have a same object but different weight, right? And I really think this will really affect like how we grasp this object. And then we don't really have such data. And I think in order to model physics, we first to have to capture such data to learn a model. And then we might think about, I'm not sure whether intelligence physics is a word I understand in my mind, but later we might be able to learn such things. But I think first we have to have the data to capture such things.
Yeah, I think maybe I can add. So my intuition with this is always that, I mean, if you model things that are passive physics, like an object falling and then bouncing off the ground, that seems like there's very specific laws that work very well. But if you have to infer the internal muscle forces that are happening that are not observable, just to model how you're going to interact with an object, it seems quite difficult. But eventually, I mean, that's what a robot would need to do. But maybe a robot would do it in a very different way, because that's very dependent on your hardware, right? I mean, how your skeleton looks like and how the torques and how you activate things.
Yeah, I agree with you. I mean, I think we really need to first have data to really capture such things, and then to learn, and then maybe we can have intelligent models to model those intelligent.
So how do we scale? I mean, you mentioned, I'm going to build a generative model to have more training data, but you need data to train the generative model in the first place.
Yeah.
So it's like kind of like a chicken and egg problem. And how do you think we have enough data sets? What is missing? And how do we, as a community, capture this necessary data?
Okay, so this question I have to borrow from Michael's comment.
Okay.
So I think there is a loop, right? So we have some models, and then we for example, we have a generative model. The generative model will help us, right? We showed actually in the grasping Fiat paper, and as well as in the CVPR paper, we showed this generative model actually help us to do recognition task, Right. So the generative model will help us to have a better recognition task performance, which means we can have more and better understanding from visual input. And then this visual input maybe further facilitates the generative model learning, right? So I think there is a loop. For example, if we have a very good synthetic hand data, which Otmar is not sure about, but assuming we have a good hand synthetic data from egocentric view, right? And then if we have such data, we can train hand-object interaction, really have good reconstruction. And then if we scale, I mean, I'm just hypothesizing everything, right? If we scale this recognition task on the YouTube videos, thousands of hand-object interaction, right? And then this is a new type of training data later for training our generative model, right? So I think there is a healthy self-improved loop could happen. Yeah.
Yeah, I agree with this. I mean, I also believe in this story, but somehow it feels like, I mean, at the end, the models are built with high quality 3D data, and then this in the wild data, which we're hoping to exploit for 3D tasks. I don't know many works that actually leverage this.
I mean, we have a very preliminary experiment for the 3D for the CVPR paper, right? So we learned this model just on the prox data set, which has 12 things and maybe 20 people, right? We learn a prior. And then what we did is, okay, given a 3D environment, right? Given an image of a person, for example, sitting on the sofa or something like that. And we try to improve the human pose reconstruction quality. And the way we did is very simple. So given this image, we try to infer the depth, we try to infer semantic, and then we can put this information into our generative model. And then what we did is generate 100 bodies given this environment. And then when we do the pose estimation, right, we don't use a V-poser, like the mean we use, right, it's basically the mean of this 100 generated bodies. So this is a this is a very simple experiment, but it shows how this generative models can later improve the pose estimation result.
But then can you now use this data in the wild to improve the generative models? That's what I'm more worried about, because they will have noise and the intersections will be not satisfied, or I don't know, there's so many complications. Sometimes I think whether there's enough signal to noise ratio when you're dealing with in the wild data to learn anything useful.
I think people are, I mean, for the human interaction cases, a 3D object, nowhere come to my mind. But for the hand object reconstruction, right? So people really putting the effort to fit, I mean, it's not an interaction prior, but manual is a hand prior, right? To fit hand models into large scale internet images. I think there is one work from UC Berkeley, Andrew, I think there is and Jitendra, so and first author is Cao Zhe. So they try to fit the hand model into this in the wild data. The result looks quite cool, and I think it's a way to, I mean, manual is learned from the scanning data, right? It's a super expensive scanner, it's high quality data. And then this data now, this prior now, people managed to use this prior to reconstruct high quality data from in the wild images. I mean, I'm not aware really about. So, yeah, I think people are moving this direction, but the work I mentioned comes to my mind. So yeah, and I can imagine this reconstructed data can further improve, for example, neural network training and recognition network. So it's.
Can I ask one last question? Unfortunately, I'll have to leave right after this. And so I wanted to thank Angela and Torsten for the invitation. This was a lot of fun. I hope soon we can do these seminars in person again, and then continue the discussions longer. So we've talked a lot about adding more and more detail. You already mentioned hair and clothing and all of this, and here I brought in physics, and so it becomes more and more detailed, right? It becomes more and more complex to model all this, both in the generative modeling side and then later in the recognition module. So why don't we try to go the other way, right? Why don't you try to go from noisy real data to very clean synthetic data, and then do the planning and control and whatnot based on very clean data, right? Which you can generate easily with, let's say, 1990s computer graphics. Would that just completely fall flat, or, you know, it seems like a domain annotation problem just the other way around, and then you make the control and planning task easier.
So I think there are works. I mean, I'm not sure whether this. So, for example, learning control policies, this kind of things from videos, from images, right? So I think at least for motion control, this line of work, I think people start to explore how to really learn motion skills from images and videos, and then learn good like control policies to animate or control the robot in a simulated environment. Is that, I mean, if I understand correctly, this is what you mean, right? So I think people start to explore that. I think that's very interesting directions. So it basically build on top of two kind of effort, right? One is people now can really have good reconstructions from videos, from images, right? So give lots of data, accurate data. And on the other hand, like people who do reinforcement learning, who do this type of like policy learning, they also make effort. So I think, yeah, it's people showing that, but to which level, like they can really leverage the in the wild data, I'm not sure.
Yeah, I think like what I think you answered the question to some degree. What I was trying to get at is that, right, like reinforcement learning itself is a super hard problem. And
yes.
The people that know more about it may excuse me if I say it doesn't work, right? Or at least it works in relatively constrained settings today, right? And so if you would try to take these methods and bring real world complexity to them, my feeling is it'll just fall over and crash and burn, right?
Yeah.
So that's why I think like, and to some degree, this is inspired by some of Thorsten's work, right? Where we try to find some level of robustness to all of this, right? The day to night kind of translation, and then trying to have one camera localization method that works for both settings. Something like this, right? For people sitting on chairs is kind of what I had in mind.
I see. Okay.
Right, so you learn how to sit on a chair that's a perfect model, a cat model, and then somehow you learn to use that policy with real world data.
I see. Okay. Yeah. Okay. I think that's I have to think more, but I think that's an interesting direction. Yeah.
We'll talk more. All right.
Yeah.
Thanks everybody.
Thank you, Otmar.
Bye-bye.
Thank you very much.
Bye, Otmar.
Awesome. I think this was a very excited discussion. So we're also just about out of time. So maybe time for one more question. At the moment, I think there were a bunch of questions on YouTube as well. So I think we can try to take a look at these ones too. Unfortunately, too many. So maybe one that is in terms of generating dynamic sequences like you were discussing. Like, I think, so the question is basically, can you go towards this kind of dynamic generation based on the interpolations through the spaces that you've learned already, or what might be missing in order to get a smooth or realistic motion sequence?
For me, I think the first challenge, there are many challenges. The first challenge is missing data. So just to my knowledge, I don't really know like really good smooth. I mean, AMAS, Gerard is part of the project, right? AMAS has really high quality motion data. It's from the motion captures, right? And from MOSH. So it's really like high quality motion. But for human interacting with the environment, I don't really see aware really like AMAS level high quality motion data. So I think the first question is, how do we capture such data? And given such data, there are also still unanswered questions, like how do we really model the interpenetration contact? How do we make sure like the human really like interact with the motion smoothly? How even do we have the representation, what kind of representation we use to do such motion synthesis? So, but I think the first challenge is the data.
I think we all want that data.
Yes.
Okay, great. Well, thank you for the wonderful talk again, and for the very interesting discussions. Also to Gerard and Omar and Torsten. Yeah, I think, thanks again.
Thank you very much, Angela, for the invitation. Thanks for Gerard for the nice, really amazing discussion. And also thanks for Torsten for the invitation. See you.